Hello dear students. So we were discussing basic solutions of a system of equations. So we have also done several problems. Now just let me give you some idea about how this basic solution looks like theoretically. Okay, suppose you have suppose ax equal to b, okay, be a system of m linear equations in n unknowns, okay, unknowns, right, where m is strictly less than n, right. So let x b represents, so let x b, or let capital B be a m by m submatrix, non-singular submatrix, okay, non-singular submatrix of capital A. Okay, that means this submatrix B actually corresponds to a basic solution, right? So we can partition the matrix, means we can rewrite the equations in such a way that, okay, we can rewrite the equations in such a way that A can be written as B together with R, where R is, so B is an m by m matrix and A contains A is an m by n matrix. Okay, so R is m by n minus m matrix, okay, submatrix of capital A. Okay, so what we are doing is actually we are just means changing the order of the variables. Okay, so something like this. So 2x2 plus 3x3 equal to 5, and if I have something like 2x1 plus 4x2 minus x3 equal to 7. So here you see, if I write it as 1 2 3 2 4 minus 1 into x1 x2 x3, this is equal to 5 7. So if I write it this way, then this 2 by 2 submatrix formed with the first two columns, okay, this is singular. The determinant of this submatrix is 0. Okay, so this is not going to correspond to a basic solution. But if I take first row with say third column, in that case I get basic solution, right, because this determinant is non-zero. 1 into minus 1 minus 3 into 2 into 3. Okay, so I can rewrite this equation as x1 plus 3x3 plus 2x2 equal to 5, and this one I can write as 2x1 minus x3 plus 4x2 equal to 7. Okay, so in that case 1 3 2 minus 1 2 4. Okay, so into x1 x2 x3, this is equal to 5 7. Okay, so here this corresponds to the B that we have written, and this corresponds to R. Okay, this corresponds to R. Okay, so the matrix A can be partitioned as B R, right, means B forms the m by m non-singular submatrix, and R forms the m by n minus m non-singular submatrix. Okay, not non-singular. R might not be a square matrix also. Okay, so we can write the matrix in this way. Okay, we can partition the matrix as this. And also we can write we write x as, so x can be written as xb together with this xr. Okay, xr, so means this is actually written as a column vector. Okay, so let me write it as a column vector, xb xr. Okay, where xb corresponds to the basic variables. Okay, xb corresponds to the corresponds to the columns of B, that is xb is the vector of basic variables. Okay, xb is the vector of basic variables, right? And xr corresponds to the columns of the matrix R. Okay, so ax equal to b will imply that a I have written it as br, and x I have written it as xb and xr. Okay, means I have taken the basic variables together and this variable together. Okay, so what is xr actually? For the basic solution, all other variables are taken to be 0, right? For the basic solution, this xr is taken to be 0, right? So since, or for the basic solution, xr is actually the 0 vector. Okay, so what happens is, so this br multiplied with xb xr, this will be equal to b, implies that, so if you multiply this as a matrix, it will be just bxb plus r times of xr. Okay, if we multiply this way, because this is a m by m matrix, this is a m by 1. Okay, this one is m by m this one is m by 1, and this one is actually n minus m by 1. Okay, so and what is r is m by n minus m matrix. Okay, so you see, when we multiply these two matrices, we get it in two parts. Okay, so this is bxb plus not plus, actually we have to write it as bxb and then r. So if we multiply this, we get a m by 1 matrix. Okay, so it's something like this. Yeah, bxb, all the first row of b multiplied with the first column here, right? First row, first column. Okay, yeah, but I have something, ax can be written as bxb plus rxr. Okay, just let us see to avoid this confusion. This is what, yeah, say for example this one here, I can write this as, if I multiply, it is something like 1 3 2 minus 1. Okay, okay, I got it. So it's something like this into x1 x2. Okay, sorry, x1 x3. So it's x1 plus 3x3, right? 2x1 plus minus x3. Okay, so we are getting this first part. Okay, and then added with the remaining part. Okay, so added with the remaining part, we have just 2x2, 4x2. Okay, so this is actually bxb plus this is rxr. Okay, so this is what is happening, right? So instead of this br multiplied with xb xr, I can always write it as because see, the first row gets multiplied with this column. So when the first row comes to the mth column, okay, so the multiplication with xb stops. Okay, next multiplication starts with the rows of, or the columns of r with this first column of xr. Okay, so this is what is happening. So it's actually bxb. So bxb, you see, if it is a m by 1 matrix, and rxr, that is also an m by 1 matrix. Okay, so this can be written as bxb plus xr is already 0, so this is 0 equal to b. So that means your basic variables are given by b inverse b. Okay, because b is non-singular, since b is non-singular. Okay, so in the last lecture also I told you that the inspiration for this basic, or the idea for this basic solution, comes from the fact that if it is a square matrix and non-singular, in that case the solution is obtained by A inverse B. Okay, so if it is not a square matrix, in that case can we obtain something similar to that? Okay, so the answer is yes, we can see something similar to that. For that we need to consider, or we need to find out a m by m submatrix from A which is non-singular. Okay, once we get that submatrix, then taking all other variables to 0, we can get that this xb equal to b inverse b is a solution. Okay, so what is the solution? Xb equal to b inverse b and xr equal to 0. Okay, these are the solutions. Means these two together give us a basic solution. Okay, so this is the theoretical idea, right? Now for a basic solution, so say some notes. For a basic solution, the maximum number of non-zero variables. Okay, the maximum number of non-zero variables is actually exactly m. Okay, there cannot be more than m non-zero variables, because we have already taken n minus m variables to 0. Okay, so this is what I am going to write. The maximum number of at most, means there are at most m non-zero variables. Okay, this is what I have to write. Yeah, thus the basic solution has not more than m non-zero variables. So for a basic solution, the maximum number of non-zero variables in the solution is m. Okay, as n minus m variables, at least m minus m variables are assigned 0. Okay, are assigned 0 value. Okay, 0 value. So it may happen that the basic variables, some of the basic variables are 0. Okay, it may happen. So a basic solution where all the basic variables are positive. Okay. Are non-zero. Okay, all the basic variables are non-zero. Is called a non-degenerate basic feasible solution. Okay, this is the short form of basic feasible solution. So non-degenerate basic feasible solution is that if none of the basic variables is 0. Okay, so a basic solution where all the basic variables are non-zero, okay, is called a non-degenerate basic feasible solution. and a basic solution where at least one of the basic variables is 0, okay, is called degenerate basic feasible solution. Okay, degenerate basic feasible solution. Okay, at least one of the basic variables is 0. In that case, we say that it is a degenerate basic feasible solution. Okay. Next, we have something called basic feasible solution. So what is that? A basic solution where all the basic variables are non-negative. That is called a basic feasible solution. Okay, a basic solution where all the basic variables are non-negative. It's called a basic feasible solution. Okay, so the vectors associated with basic variables are always linearly independent. Okay, so this is already we had discussed, right? So a basic solution where all the basic variables are non-negative is called a basic feasible solution of the LPP. Okay. So similarly, a basic feasible solution is said to be non-degenerate if all the basic variables are positive. Non-zero. Okay, a basic feasible solution is said to be non-degenerate if all the basic variables are non-zero, right? And if at least one of the variables is 0, then we say that the basic feasible solution is degenerate. Okay. So this is already there. Okay, so this was about basic feasible solution. So let us see one more example. Okay. Yeah. So if we try to find out something, yeah. So let us see whether these are basic feasible or not. Just one or two more exercises. Find all the basic solutions. Find all basic solutions and discuss their nature. Okay, discuss their nature. For the following system. Okay, what is the system? 2x1 plus 3x2 minus x3 plus 4x4 equal to 8. Okay, and x1 minus 2x2 plus 6x3 minus 7x4 equal to minus 3. Okay, so this is the system of equations. Okay, so here how many columns are there? 4 columns are there. Okay, and out of these 4 columns, since there are only 2 equations, so we have to select 2 columns at a time in order to choose 2 by 2 non-singular submatrices. Okay, so we write this as this. here A equal to, A is the coefficient matrix, 2 1 3 minus 2 minus 1 6 4 minus 7. Okay, A is this, right? So the maximum number of or let us write the number of principal or submatrices, 2 by 2 submatrices, 2 by 2 submatrices is what is equal to, so there are 4 columns. Out of that I have to select 2 at a time. In that case I will get the number of 2 by 2 submatrices. Okay, so these are what this 4C2, so that is actually 6. Okay, so there are 6 possibilities. Okay, so let us choose one by one. So B12 means I have chosen first column, second column. Okay, so this is equal to determinant of B12 equal to determinant of 2 3 1 minus 2. Okay, so which is minus 4 minus 3, so that is minus 7, which is not equal to 0. Okay, so B12 corresponds to a basic solution. Okay, responds to a basic solution. So how will you find out this solution? So B12 corresponds to which two variables? X1 and X2 only. So we have to take X3 and X4 0, right? So taking X3 equal to X4 equal to 0, we get, so what do you get? 2x1, so let me write it in matrix form, 2 1 3 minus 2. Okay, 2 1 3 minus 2 times of x1 x2, this is equal to, the right side is same, 8 minus 3. Okay, so that means x1 x2 is nothing but this inverse, 2 1 3 minus 2 whole inverse of 8 minus 3. Okay, so you try to compute this. What is the determinant? Determinant is 1 by minus 7, right? And to compute the determinant, what you have to do, just change the signs of this diagonal entries and interchange the this off diagonal entries, because cofactor of 1 here will be just change the signs of the okay, wait, cofactor of 2 is minus 2, it's okay. Sorry, what did I say? In general, what is the inverse of ABCD? Okay, ABCD whole inverse is actually 1 divided by AD minus BC, and then you see the cofactor of A is D, right, and cofactor of D is A, and cofactor of B is minus C, so cofactor of B actually comes here. Yeah, so this is the general rule actually for a 2 by 2 matrix. In order to find inverse, just divide it by the determinant and then interchange the diagonal entries. Okay, just interchange the diagonal entries and change the signs of the off diagonal entries. Okay, so here we have interchanged the sign diagonal entries, and we are changing the sign of the off diagonal entries. Okay, so whatever we get, that is the inverse. So 1 by minus 7 multiplied with, if you multiply this, it's minus 16 minus plus 9. Okay, and this is minus 8 plus minus 6. Okay, so it's actually minus 1 by 7, this is minus 7, and this is actually minus 14. Okay, so if you just simplify, this is 1 2. Okay, so this gives us a basic solution. So therefore x1 equal to 1, x2 equal to 2, and x3 equal to x4 equal to 0. Okay, so this is a basic solution. So here you see not only it's a basic solution, it is also non-degenerate. Okay, also it is a basic feasible solution, because the variables here are non-negative. Okay, so it is also a basic it is also a let us write non-degenerate also, because the basic variables are non-zero. So it's a non-degenerate basic feasible solution. Okay, not only basic solution, it's a non-degenerate basic feasible solution. Okay, so that is the complete answer. So for the first case we have solved. Okay, the second one is we take B13. Okay, so we have started with first row, first column, second column, then we'll go to first column, third column. Okay, so B13. What is B13? If you see from here, it's 2 1 minus 1 6. Okay, so B13. Okay, so B13 is B13. If I take the determinant, so this is exactly equal to 2 1 minus 1 6. So it's determinant 2 1 minus 1 6. So if you compute this, it's coming out to be okay. So it comes out to be this one, 8 minus 12 minus plus 1. Okay, so this is 13, which is non-zero. Okay, so B13 corresponds to a basic solution. Corresponds to a basic solution. We can find a basic solution for this, right? Basic solution. I don't know whether it's feasible or not, but I know it's a basic solution. Okay, so which two variables we have to take 0? So taking, see, from here itself you can see this B13 corresponds to x1 and x3. So we'll take x2 equal to x4 equal to 0. Okay, we get. So what do you get? Just from here itself you can write 2 1 minus 1 6 multiplied with x1 x3. Okay, this is equal to 8 minus 3. So if you simplify, x1 x3 is actually equal to this 2 minus 1 1 6 inverse of 8 minus 3. Okay, so the inverse is actually 13, 1 by 13, and then interchange the diagonal entries and change the signs of the diagonal entries. 8 minus 3. Okay, so it's 1 by 13 into 6 is a 48. 48 minus 3 is 45, and this is minus 8 minus 6, so it's minus 14. Okay, so it's 45 by 3 and minus 14 by 3. Okay, so here also basic variables are non-zero. So here x1 equal to 45 by 13. So sorry, this is 13. x2 equal to 0. x3 equal to minus 14 by 13. Then x4 equal to 0 is a, so it's a basic, we know it's non-degenerate. Okay, is non-degenerate basic solution. Okay, it's not feasible, right? It's just a basic solution because here one of the variables is negative. Okay, so it's a basic solution, it's not a basic feasible solution. Okay, right. So next one is, just you can see 1 4. Okay, if I collect 1 and 4, okay, in that case what will happen? So if you go to 1 4, B14, this determinant, this is actually equal to 2 1 4 minus 7. Okay, so 2 1 4 minus 7. So this determinant is minus 14 minus 4. So that is minus 18, which is also non-zero. Okay. So taking, so this B14 also corresponds to a basic solution. So taking x1 equal to x2 equal to x3 equal to 0, we get this 2 1 4 minus 7 multiplied with x1 x4. This is equal to 8 minus 3. Okay. So if you simplify, it's x1 x4 equal to 2 4 1 minus 7 inverse of 8 minus 3. Okay, so it's 1 by minus 18 multiplied with, just interchange the diagonal entries and change the sign of the diagonal entries. Okay, of course for a 3 by 3 matrix is difficult. Usually 3 by 3 matrices do not come for this type of problem. Okay, for 3 by 3 matrix, what is difficult is just means finding out the determinant and computing the inverse. Okay, that is the thing. Otherwise it's simple. So it's minus 7 into 8 is minus 56. Minus 56 plus 12. Okay. So what is that? Minus 44. Minus 44. Okay. Minus 44, and then here is minus 8, minus 6, minus 14. Okay. So here also it's non-degenerate, but only basic solution. Okay, it's not feasible. Okay, so that way you have to solve. So I hope the others you can do it. Means you have to try this 2 3 and 2 4 and then 3 4. Okay, so these are the things that you need to try. So please complete these things. So I'll give you some exercises which you may try. Please try those things. Say okay. Say this one. Find the basic solution with x3 as a non-basic variable. Non-basic variable. That means what? You have to put x3 equal to 0. So it's simpler. Okay, in the earlier problems we had to find all basic solutions. Okay, that's not the case here. You are just asked to find out if there is any basic solution corresponding to x3 as non-basic variable. Okay, 5x1 plus 2x2 plus 3x3 equal to 4. Okay, so let me give you the answer also, so that you can, after you do it, you can be clear. X1 equal to 5 by 9. The answer may be incorrect also. I am just giving it from the book. 11 by 18 0. Okay, so this is from your textbook only. Linear Programming and Game Theory by Chakravarti and Ghosh. Okay, so please try this problem and see whether you get the same result or not. And then another one, find the basic solutions of x1 plus 2x3 equal to 1, x2 plus x3 equal to 4. Okay, so you have to be very careful here. Here there are 3 variables actually. Okay, at a first glance you might be misleading, means you might be diverted from your attention that there are 2 variables. Okay, there are actually 3 variables, x1, x2, x3. So the first one is x1 plus 0x2 plus 2x3. Second one is 0x1 plus 1x2 plus x3. Okay. So find the basic solution of this, and discuss their nature. Okay, and discuss their nature. Nature means whether they are non-degenerate or whether they are feasible or not. Okay, so the answers also let me just provide so that you can verify. I'm just writing it 0, 7 by 2, 1 by 2. Okay, this is one solution. Another solution is minus 7, 0, 4. Another is 1, 4, 0. Okay. So these are the solutions. So you can just try it out for yourself and match with the answers. Show that all the basic solutions of this 2x1 plus 6x2 plus 2x3 plus x4 equal to 3, 6x1 plus 4x2 plus 4x3 plus 6x4 equal to 2 are degenerate. Okay. Show that all the solutions are degenerate. Okay, so these problems, please try these problems at at home. So in the next class we will start with another part of the same unit, that is characteristics of an optimal solution, that is convex sets and their properties, and a few theorems which will be necessary for our further study of LPP. Okay, so till then, bye.